People online can hear us and can ask questions as well. So we have to make sure at the end of each presentation we get to give those a chance to ask their questions. It's always a standing EURADOS joke that I'm going to be so hungover after the dinner they'll give me the 9 o'clock session. So anyway, here we are, and I actually made it on time. I'd like to welcome you. It's a very exciting program, I think, today on medical dosimetry. A city with a lot of medical facilities, one of the best in the country. So I'd like to start, not waste too much time since we're already a bit delayed. The first presentation is from Hans Rabus. And I'll just check his title exactly. Some aspects of dosimetry for radiobiology. Hans is the chair of Working Group 6 and on numerical dosimetry, and an expert in dosimetry for radiobiology. So anyway, Hans, I'll leave it to you.
Okay. Thank you very much, Rick. Good morning, everybody. I'm very pleased that you all made it in time. In fact, while we are starting, I can just relate that I was asked to give this presentation based on the ground that I gave a similar presentation 5 years ago, and oh, do I have to start?
No, we will do it.
And I couldn't remember what this presentation was about, so I hope today I will remember. And it's this hour. Okay, great. So, some basic aspects of dosimetry for radiobiology. When we talk about biological radiation effects, coming to them is actually taking a lot of time, or it's actually spanning several orders of magnitude of time, starting from the early physical effects, which take place on the order of attoseconds, and then within about femtoseconds you are producing radicals. These radicals can diffuse, you have chemical reactions, and at some point you really have induced a damage in your biological system and repairs it in. And then it still takes from microseconds to seconds before you really come to the point where you can see a biological effect. And sometimes it takes even days or even years to see that effect. So we start from the, do I have a laser pointer, Liliana? Okay, good. Oops, no, that was not the right one. Go back. Yes. No, and this way I'm moving forward.
Let's.
Okay.
1 second.
Yes. Okay, great.
I will figure it out how to use it.
Yes. Take it away from me. All right, so essentially we start from something where we have a distribution of energy transfer points. And in the end we end up at something like this on this one. I see, okay. Anyway, on the cellular scale, and these are DNA double-strand break repair foci. So what my presentation will be about is, it will have two parts. One is how does dosimetry relate to the biological outcome? And the second part will actually be how the biological outcome depends on other physical factors than those. So a typical biological endpoint is cell survival, clonogenic survival. So you irradiate your cells to a certain absorbed dose, and this can be absorbed dose to water, usually. It can also be absorbed dose to tissue. Sometimes in many of these experiments, it's in reality air coma that they are giving as dose. And you have the surviving fraction, which is a proportion of cells that survive after a certain period of time. And if you plot that on this ln-log scale, you actually get this, parabolic curves here, and you see actually that these curves are different for different radiation types, different radiation qualities. And if we then compare the dose that we need with a given reference quality to the dose of the radiation quality we are interested in, we can define something like a relative biological effectiveness, which always refers to a certain type of radiation and to a certain biological endpoint. All right, so what you actually see when you do this data fitting to your measured points is that it's actually the parameter alpha of this linear quadratic relation that is changing, while beta is usually not changing too much between radiation qualities. And the question is why? Why is this so? So the usual answer is because the LET increases. And what does this mean? It basically means that you have a higher ionization density. Okay. And where does this actually show up? What are the results of this? Of course, you can say the biological effect is where it shows, but in fact, it shows at a more elementary level. It shows up at this early stage of radiation interaction in the form of the so-called chemical heat effect. And I will explain now shortly what this chemical heat effect is about. So I have to go back to really the realization of absorbed dose. So absorbed dose to water is usually realized with so-called water calorimeters. And this picture shows a water calorimeter that was in operation at PDB about 25 years ago. I'm not going into the details too much, but essentially what you have there, you have an absorber, a volume of water, and you have some thermistors to measure the temperature. And then you measure the temperature as a function of time. So here's time, here's the temperature change. And here you switch on your radiation and you introduce energy into your system by the radiation, and therefore the temperature rises. The temperature rise is proportional to the absorbed dose, approximately proportional. And the proportionality factor is simply the heat capacity. Very nice macroscopic quantity. And the inverse of this heat capacity for water is just 0.24 millikelvin per gray, and this tells you already that this is a very challenging measurement. So if you want to convert this approximate identity to a real identity, you have to apply correction factors. And the correction factor that is most important in that case is a factor which is almost unity, but has this small deviation from unity, and this is the chemical heat effect. Okay, still I have not told you what the chemical heat effect is. Let's first look how this heat effect depends on the linear energy transfer. So here is plotted linear energy transfer, chemical heat effect, and different ion types at different energies, therefore they have different LET. And you see that you have here something on the order of 1% to about 5%, a few percent. So this chemical heat effect is the fraction of the radiation energy that you introduce to your system that is spent into persistent chemical changes. So it's produced, used to produce irreversible changes that are not ending up as heat and as a temperature rise. And one example of these persistent chemical changes is damage to biological molecules. Of course, looking at the survival curves is then a little bit inconvenient, so you may want to look at effects that are more directly related to the damage that you are introducing, and I show here as an example, measurements on the mutation frequency as a function of absorbed dose. Again, for two radiation qualities, here gamma rays and neutrons. And essentially the slope or the asymptotic slope of these curves is related to the chemical heat effect. Okay, so conclusions of this first part are determining absorbed dose to water either in tissue or in water is challenging, but it does not necessarily give you the information that really pertains to the biological consequences. the major part of the energy that you put into a system by radiation is transformed into heat. And heat itself is not damaging the biological system, at least at the dose levels we are talking about. And this small percentage of energy spent on persistent chemical changes is what determines biological effectiveness. All right, so now I've talked a little bit about these cell assays. So in principle, if we do cell irradiation, we have different options to doing that. And one of the most elegant options, which also gives us a little bit more insight on how the radiation quality affects the biological system, is to do this irradiation with microbeams, with ion microbeams. And this is a schematic view of the microbeam that is or has been in operation at PTB. Essentially, you are attached to an accelerator, you are extracting ions at a very low fluence rate, such that individual ions are actually exiting your vacuum system through the exit window here, and attached to that exit window you have adherent cells, which you then irradiate individually. And down here you have a photon detector to detect the fluorescence that is produced when the ion goes through the exit window to register that an ion has arrived. We used this ion beam in the BioQuad project to do cell experiments where we were irradiating, targeting individual cells in such a way that they were traversed by five ion tracks, one in the center of the cell and 4 at the corners of a square. So, and now if you want to really understand what's happening in such an experiment, we have really to think about what is actually the object we are investigating. So what I show you here is one of the slides from a micrograph that you take there. You simply do microscopy, you take a photo of that, and this is just one section of it, 400 micrometer side. And you see these gray things there, which are basically cells that have been stained to make them visible. So if we now zoom in a little bit more, we see here actually 3 different cells. And this is just, and you see that they have a very different cross-section. And in fact, if you do that over the whole ensemble, you see that the cross-sectional area has a quite broad distribution, as you can see here, by almost 50% relative standard deviation. And of course, this has consequences, because now if you put your ions there, you actually have the situation that in some cases, like here, the ion may actually miss the cell nucleus, so it doesn't do any, it does do damage, but not to the cell nucleus. And what is even more important, you have different short length distributions. So the path that the ion travels in your system is different. And this is actually something I would like to go a little bit deeper into. So, and for that, I will actually make an assumption, starting with an assumption, that we are able to do an ideal experiment, which is usually what the people do when they do simulations. So we are absolutely precise in our targeting. And okay, I wrote here cylindrical shape of the nuclei. This is often assumed when people do simulations, but of course the question is such a nucleus cylindrical? Usually, probably it would be more likely that it is an ellipsoid. And the second question is really, what is about the third dimension that we are not seeing here when we do microscopy? And so basically, this is now just some theoretical consideration. So again, we start with an ideal irradiation, and ideal irradiation we would actually align this pattern so that it aligns with the orientation of the cell. And then we have actually to make an assumption about the thickness of the cell, or what is happening in the third dimension. And one very trivial assumption is, okay, all the cells that we see here have the same thickness. So what I will do in the following is I will actually introduce a coordinate system and show you cross-sections through these cells in these respective coordinate system. So we have the x-axis will be labeled in red, the y-axis in green, and the z-axis in blue. In this graph, the z-axis is coming out of the plane. If we now attach these coordinate systems to the cells, and now look at the other sections to these cells. So here we have the xz, which is then this plane. And on the right-hand side, we have this plane. Okay, so it's not really spectacular. I mean, you plot a cut through an ellipsoid, you get ellipses, okay? If I do that for this guy here, it's essentially the same, and for this as well. And the important thing is now, of course, I made the assumption they have all the same thickness. Therefore, the ratio of the height in this direction of this ellipse and the z-axis arrow is the same for all three. And in all coming plots, the length of this z-axis arrow will be the same, but I will make different assumptions of what's actually what kind of objects we're having. And being a stupid physicist, of course, I see something is just scaled in 2 dimensions. Okay, but why isn't it scaled in a 3rd dimension in the same way? So if I do that and start again with this case of the upper cell, and then I choose this cell which is smaller, has a smaller cross-section. If I make the assumption that it scales in all the 3 dimensions, of course, this cell gets oblate. And the one with the big cross-sections gets prolate, as compared to the one on the top. Okay, that is probably not the best assumption, and again, being a physicist, assuming that, okay, we have a cell nucleus. It contains the DNA, which is more or less the same always. It has a lot of water, it has a lot of proteins in it. So, but in the end, it should be more or less the same all the time, and therefore it also should have the same volume. And if we do that assumption, of course, we get something completely different. If the cross-section shrinks, the cell gets prolate in the 3rd dimension, and if the cross-section increases, it gets oblate. So what does this mean in terms of track length distribution? So I first show the case that I've not shown on the previous slide. So I now assume that the cell is actually cylindrical. So if I do a cross-section along the cylinder axis, I see a rectangular cross-section. And the track length distribution in the case of the same height is just here. I mean, everyone has the same height. Okay. If I assume that they have the same volume, of course, and I'm just showing the ensemble average over these 3 cells I showed in the previous slides. Then, of course, I get a distribution like this. 1/3 has the probability of having higher, 1/3 of lower, and for the same scaling, it's similar but shifted. So that was the simple case. That is what usually people do in simulations. If we actually assume that the cell is an ellipsoid, then things get a little bit more complicated, because the ions that are not in the center of the cell, but at the edges of the square of the irradiation pattern, they actually go through a thinner layer of material. So you get then a distribution that is a little bit broadened. And in fact, you can see here that it's almost a factor of 4. That is, that can occur here as changes. And how does this actually affect now the outcome of your experiment? So this is now showing on the left-hand side here with the black background. That's really results of measurements. You don't see these 5 pattern because it was done with an experiment, so not as ideal as the simulation. And basically what we are seeing here is DNA repair foci that are produced by ions going into the image plane. So DNA damages that are formed along the track of this ion are basically at the same location. And as these DNA repair foci have an extension on the order of micrometer, 1 micrometer or half a micrometer, they are basically overlapping and are indistinguishable. So what we are seeing here is, we are seeing the spots where an ion passed and produced at least one DNA double-strand break. And it's quite straightforward to calculate what is the probability for this to occur. It basically gives you this relationship that this probability that a foci is formed where an ion passes is 1 minus the probability that no interaction occurs or no DSB is produced. And here the track length enters. And of course you have a proportionality factor, which is basically the number of DSBs per unit length of the part. So in the case that you have loosely ionizing radiation, it can happen that this prefactor is actually very small, so that you can actually expand this exponential, just to do the Taylor expansion, just take the linear term. And then, if you do the average, you will actually see basically the average track length. But as with ion beams, this is usually not the case. And if you then change the value of L by a factor of 4, you get a completely different probability. And what you have to do in the end is to average over the probability and not over the track length. So, and of course, I said already, the experiments here were of course done with a real ion beam. And with a real ion beam, of course, you are not hitting exactly at the spot where you want it to hit. You actually have essentially a Gaussian distribution about your target position. And if you overlay that, you get something like this. So it's a kind of broad distribution, and the track length distribution, of course, gets continuous and smeared out. So, conclusions for the second part. Getting the dose, which is an expectation value, getting it right is challenging, but it may not be the whole story. A large fraction of the variance observed in radiobiological assays may actually be due to the physical characteristics of your experiment, and they are currently not part of the observation. And there has been lots of articles about reproducibility crisis and so on. This reproducibility crisis may actually be somehow due to the physicists. And just as a side remark, yesterday morning on a completely different topic in our joint session with Working Group 11, we were discussing about unfolding of neutron spectra from bonosphere measurements, where basically, of course, the position of the bonosphere in the room where you do the measurement is very important and gives you a variability that will then actually spoil your results. And that's completely parallel to what we are having here. And so these parameters are something like the shape and the size of your geometrical object and the relative location of the tracks and the cell nuclei. And measuring this information could actually provide a better quality of radiobiological results. So, as my overall summary, these were many of the slides I showed today. So, in the first part, I wanted to convey the message that absorbed dose has its limitations. And in the second part, I wanted to say that part of the biological variance is due to physics. And so I hope I have not spoiled the day, because it's all about the symmetry today, but I cordially invite your questions. Thank you.
Thank you, Hans, for a very, very interesting presentation. And after the last time when Hans chaired us at EURADOS school and I overran by about half an hour, incredible timing. Of course, this is a school, and you're not supposed to leave here not knowing things and claiming your CPD points. So if anyone's got any questions, can you please put your hand up, and I'll then go to the online questions as well. Any questions from the audience? Yeah. Yeah, I need to do microphones so the people online can hear your question as well.
And me as well.
Have you also tried to investigate, during the cell cycle. It does not necessarily stay in the same shape. At some point, there's a how that would impact your results.
Yeah, you're right. Actually, I did not tell everything. These experiments were actually done with synchronized cells, so that they were on the GCO G1 phase.
Very good talk. My question is, absorbed dose, of course, has its limitation. Because absorbed dose, I mean...
What is the question?
The question, of course, has its limitation. Because the absorbed dose depends on the volume size.
Well,
I mean, to relate to the effects. Then we go to micro.
Yeah, I mean, basically, you're absolutely right.
Yeah.
One has to go beyond this. I mean, absorbed dose is an expectation value, and one really has to understand that, because you can have situations where you have a high probability of having no interaction in your volume and a small probability of it occurring. Then you still have an expectation value of the absorbed dose, which is quite low, but which is completely irrelevant, because you have what makes the change is that interactions occur. Yeah, thank you for that comment.
One last question from the audience, from Gunther.
Yes, thank you very much for this nice presentation. Yeah, and you are right. Part of biology variance always due to physics, but the bigger part is due to the biology. Yeah, because as you explained, really nice that you measure at different places with the spinospheres. Yeah, where's your target? Yeah. And this is the location of the target.
Yes.
You never know whether you hit really the target. And this is a big uncertainty, yeah, because the dose distribution around your tracks, of course, is different, yeah, for if the target is at a different place, yeah.
Yeah, I mean,
so that's what you implemented, of course, yeah. Thank you.
I mean, basically, if you do an ordinary cell experiment where you do broad beam irradiation, you don't know this relation. Yeah. Thanks. Yeah.
Thanks very much, Hans. A very interesting presentation. It seems like the people online are asleep, so there are no questions from people online. Okay. The next speaker is Anna Subiel from, I hope I'm pronouncing your name correctly, the National Physical Laboratory. We'll be talking about dosimetry for flash radiotherapy, which has been a hot topic this week.
Good morning, ladies and gentlemen. First of all, I think I gave a bit of scare of the organizers, because I arrived here well ahead of time, but turns out I have been directed to a wrong room. And I realized after the first couple of minutes when the meeting started that I'm in the wrong place. But here I am, and I'm hoping to tell you a little bit more on challenges of dosimetry for flash radiotherapy. I have here my timer on the side, so I'll be occasionally glimpsing if I'm not overrunning, to make sure that we have a little bit of time for questions as well. So that's the outline of the talk. I very briefly go through it because I want to concentrate on the concrete examples. Just for those who haven't heard much about flash, I'll just give you a very, very brief introduction. What is flash radiotherapy? Remind you of the importance of traceability for radiotherapy treatments. Then I'll give a bit of background on reference dosimetry, specifically looking at the TRS 398 code of practice and how potentially we could think of applying this existing code of practice for dosimetry in flash. And then I'll give you a couple of examples of the current developments of detectors that could potentially be future secondary standard instruments for flash radiotherapy, and a bit of work that have been done so far on employment of primary standard instrument for ultra-high dose rate exposures before summarizing. So currently we are delivering radiotherapy, or since really last century have been delivering radiotherapy in this fractionated scheme. And the whole idea behind it is to give a normal healthy tissue the time to recover the radiation damage while still maintaining the tumor control. However, flash radiotherapy is a paradigm shift. It's a total different way we want to deliver radiotherapy. That type of delivery is relying on delivering radiation in a very, very short time, just in a fraction of the second. And it has been shown that this approach is leading to remarkable reduction of normal tissue toxicity with respect to conventional radiotherapy, so the radiotherapy we are delivering currently to the patients. Let me just highlight that the term flash is not being used to describe the parameters of the beam. Flash is being used to describe the biological effect, so the effect that is related to normal tissue sparing. Interestingly, the first ultra-high dose rate exposures are dating back to the 1960s. We are not too often relating to those experiments, but in the matter of fact, these are the first times that it has been demonstrated that the delivery of ultra-high dose rate to healthy mammalian cells is sparing normal tissues much better than when delivering in a conventional dose rate levels. However, for a long, long time, another 50 years, we haven't seen much work done in this field, and it was all related to the fact that we had very limited access to this type of radiation sources. And then in 2014, we had the seminal paper published by Vincent van Vanten and his colleagues from Schuf in collaboration with Institut Curie that demonstrated that thoracic irradiation of mice, let me just grab here a laser pointer, thoracic irradiation of mice to ultra-high dose rate electron beams is significantly sparing normal tissue toxicity. In this case, it was the pulmonary fibrosis that was this endpoint looked at, with respect to conventional dose rate delivery. And since then, we had a number of preclinical studies demonstrating similar effect, and this is another example from Marie-Catherine Vosna, demonstrating that delivery of ultra-high dose rate radiation, really high dose levels, you can see of the order of 28 to 34 gray, is significantly sparing the tissue, the healthy tissue. In this case was a skin pick, several weeks, 48 weeks post-irradiation. While in the case of conventional radiotherapy delivered at 5 gray per minute, you can see these obvious necrotic lesions at the surface of the skin. And since then, we had also patients being treated with this ultra-high dose rate radiotherapy. So the first patient had a UHDR electron beam treatment in 2019, and he has been treated, this patient, for subcutaneous lymphoma. And as you can see, 5 months post-irradiation, we have hardly any side effects that are visible. Since then, we also had a first proton flash clinical trial that has been already completed at the end of 2020. This was just a feasibility trial, which has been treating, in this case, 10 bone metastasis patients. And there have been already some published results showing that feasibility is certainly there. However, what I wanted to highlight, the main focus currently related to flash radiotherapy is being really around radiation biology. This is, in fact, the area that is driving this research forward. The fact is that we still really don't understand what is the underpinning mechanism of the flash effect. And I wanted to quote here one of the pioneers of flash radiotherapy, John Lee Henry, who said that there is a wealth of future studies that are waiting to be done at all levels of physical, chemical, molecular, biological, and chemical endeavors. However, I want to highlight that if there is an error made in dosimetry, in the dosimetry, that difference between conventional and ultra-high dose rate exposure may be due to the fact that we really didn't understand and didn't really carry out the proper dose measurement, not really due to the flash effect. So what is currently a requirement for accuracy in dosimetry? So for instance, ICRU report 24 is stating that uncertainty of 5% at k equals 1 is tolerable in the delivery of the absorbed dose to the target. However, I want to highlight that this 5% is the overall uncertainty, which includes several aspects, including dose delivery, dose calculations, patient's positioning, and so on. So it means that the dose measurement at the reference conditions of this best defined conditions should be within 1% at k equals 1. And that's just a very brief reminder of the importance of traceability in radiotherapy. So the term I'm pretty sure everyone is very familiar with. But it is, again, transferable and needs to be also applicable to all the new modalities that are emerging, like flash radiotherapy. So we need to remember that traceability is this unbroken chain of calibrations, as you can see over here, with which each of those calibrations is contributing to measurement uncertainty. And we need to make sure that we are able to demonstrate those traceability chains, not only for the existing therapies, but also for emerging ones like this one, if we want to successfully implement those type of therapies to clinical practice. So looking now at dosimetry code of practice, given that this is international community, I just decided to focus purely on the TRS-398. And the TRS-398 formalism is applicable only under those reference conditions. So I just, this is not to pay attention to details, it's just to grab the snapshots from TRS-398 demonstrating that there is very well-defined conditions, reference conditions for each beam quality, which needs to be fulfilled in order to carry out reference dosimetry for different beam qualities. And TRS is so-called the KQ formalism that enables us to derive the absorbed dose to water in our beam quality, in the user or clinical beam quality, by employment of this, this relationship, where we have a ionization chamber reading corrected for temperature and pressure and polarity. We have our ion chamber calibration factor, beam quality correction factor, and I decided to put explicitly on the side ion recombination factor, which quite often is being embedded within this quantity. However, it will be important in the context of flash radiotherapy. So let's have a look at the ion recombination at this first. So ionization chambers are our gold standard instrument used currently in radiotherapy, but the fact is that under influence of ionizing radiation, we'll be expecting effects such as ion recombination, so ion pairs generating in the volume of the ion chamber will start recombining. We have here two different routes of ion recombination, but the one that I want to draw your attention because it's the most relevant and the most will have the largest implication at ultra high dose rate exposure is so-called general recombination, when ion pairs from different charged particle tracks are recombining with one another. And that type of ion recombination is dose rate or dose per pulse dependent. Let's have a look for a moment at the different type of beams that have been so far the most commonly used for delivery of flash radiotherapy. So probably most of the studies that have been published on flash have been demonstrated with low energy electron beams, and this is the typical temporal beam structure of the electron linacs. For proton beams, we could have two options. We can have proton beams generated with isochronous cyclotrons with the pulse repetition frequency of the order of 70 megahertz, or on synchrocyclotrons with a PRF of the order of a few hundreds, 500-600 hertz. So you can see that actually all of those beam modalities have some sort of pulse structure. But from the point of ionometry, the beams are considered to be pulsed if the pulse duration is comparable or larger. If the pulse is comparable or larger than the pulse duration of the beam itself. So if you look at those different temporal beam structures, actually that electron beam is pulsed beam from the point of view of ionometry, as well as the proton beams accelerated with cyclotrons. However, this is a quasi-continuous type of beam, so it means from the point of view of ionometry, it's actually behaving like a continuous beam. So for the conventional dose rates, we have very well established theories and formalisms, how we can correct for this ion recombination effects. In the interest of time, I cannot go into details, but I wanted to highlight that we have challenges related to applicability of those established formalism at ultra high dose rate beams. I'll go back into ion recombination in a moment, but I want to just bring up the other factor that is important for reference dosimetry from the point of view of TRS-398 formalism, the KQ factor, which is the factor that is correcting for the difference in the ionization chamber response between the reference and our clinical or user beam quality. And we can evaluate those factors using Monte Carlo methods by calculating so-called FQ factors, and which is essentially FQ factor is the relationship or is the ratio between the absorbed dose to water in the absence of any detector divided by the dose to the cavity of the, in this case, ionization chamber. And the KQ factor is this relationship, the ratio of the FQ factors multiplied by the ratio of the WR values that are being tabulated in ICRU 90. We can also determine those factors using experimental methods, but this does require us access to primary standard instrument that can disseminate the quantity of interest in absolute terms. So experimentally, just wanted to draw your attention, experimentally we also will need to evaluate the ion correction factor, ion recombination correction factor in order to have experimentally evaluated the KQ factor for a given ionization chamber. Okay, let's move on now to dosimetry at ultra-high dose rate beams, starting with the pulsed electron beams. So the talk that I'm giving today is supposed to be around challenges of dosimetry in this new type of modality, and that slide is probably the key point to demonstrate that challenge. So as I already highlighted, ionometry is a golden standard used for reference dosimetry, but also ion chambers are being used widely as beam monitors across the different beam modalities. So it is really critical technology that is being employed in everyday beam delivery of radiation to the patient. But what the slide is representing, it's a work that has been done by my colleague Christopher Peterson from Oxford that has demonstrating the behavior of a typical secondary standard ionization chamber used for electron dosimetry when operating it at ultra-high dose repulsed beams. So what is on the y-axis is so-called ion collection efficiency, and we can see that when we are operating at the conventional dose rate levels or the conventional dose repulsing curves of electron levels, the ion collection efficiency is essentially 100%. However, when we start approaching the ultra-high dose repulse regime, which is typical for the flash radiotherapy, this instrument is exhibiting very, very large ion collection losses. As you can see, in some cases going down to 50% collection losses or even 70%. And it's due to the ion recombination I just described before. Christopher was trying to suggest, there may be some empirical way to correct for this behavior of the chamber, and he suggested that it's possible to use this logistic formula that is relying on the fitting of two parameters, alpha and beta. However, this is really not physical representation of what is happening with ionization chamber. Hence, it wouldn't be ideal situation or ideal way to be used in a clinical configuration. I'll have as well a bit of extra work, but towards the end of the talk on ionometry in quasi-continuous proton beams, but if you can hold on with me for a moment. So going back to TRS-398, I wanted to highlight that could be two possible routes for reference dosimetry in flash radiotherapy, with the aim to still employ the formalism that is already existing. For instance, we could use possibly existing ionization chambers and accept larger ion recombination factors, for instance. However, this would require development of new methods for determination of those factors. And the question that arises is still what level is acceptable, and are we able to measure this ion recombination factors with uncertainties that we are currently measuring in conventional radiotherapy? The second option could be to use a different dosimetry solutions, which won't be suffering from dependence on dose rate or dose per pulse. However, this will require determination of the beam quality correction factors, KQs. It would mean then that we would need to be able to determine those two factors, KQ and KS, which I just described, and still being able to use the formalism that has been described in TRS-398. So let's have a look now at the new dosimetry solutions that have been proposed for flash radiotherapy, starting with ionization chambers. This work has been done by my colleagues from University Santiago de Compostela, here explicitly by Faustino Gomez. So Faustino started his initial investigations raising a question how we could change design of ionization chambers and make it still relevant for flash radiotherapy. So Faustino started with simulations of ion recombination. In this case, he carried out simulation for a plain parallel ionization chamber operating at 300 volts and 5 gray per pulse. And he demonstrated that if we decrease the distance between electrodes significantly, we actually can alleviate problems related to ion recombination. And he came up afterwards with the first prototype of so-called ultra-thin ionization chamber, which had electron gap separation below 300 micrometers, in this case 270 microns. And just to guide your eyes where current ionization chambers that are being commercially available are sitting on that graph, you can see those chambers will be exhibiting very, very large ion recombination effects for this experimental configuration. So following up on work made by Faustino, PTW, the dosimetry company, has taken forward that approach and has manufactured a number of plain parallel ionization chambers with different gap separation ranging from 1 millimeter down to 250 microns. And indeed, they have demonstrated that for the thinnest ion chamber, so with the thinnest gap separation ion chamber, in this case 250 microns, you can see that the measured dose per pulse as a function of reference dose per pulse is maintaining this linearity across very large range of dose per pulses. And it was also demonstrated that if additionally we apply existing ion recombination correction factors, so employing the current formalism, we actually can achieve the linearity within 0.2% across this whole range of dose per pulse. So ionometry could be potentially still a method for dosimetry in flash radiotherapy, but diamond detectors as well are available. And I mean, maybe without going into details, the diamond detectors are still very relevant and interesting detector because they, of course, do not suffer from ion recombination effects. They are close to water equivalent, have a good spatial resolution and stability. So the starting point for PTW, that is currently the manufacturer of the microdiamond, was to investigate the response of the currently existing microdiamonds in a high dose per pulse range. And this work has been led by Raphael Kranzer, who has shown that when operating different prototypes of microdiamonds, there is always linearity at a low dose per pulse range, and then depending on the type of the microdiamond, this linearity is being broken. There started to be deviation at a higher and higher dose per pulse. So Raphael started looking at the reason, and turns out that it is very much dependent on the size of the active area of the microdiamond. So he demonstrated that just simply by making the smaller size, smaller area of the microdiamond, it's possible to extend the range of linearity for the instruments in ultra-high dose rate beams. But another step has been taken by original developers of microdiamonds from University of Tor Vergata, Marco Marinelli and Gianluca Veronarinati, who have demonstrated that apart changing the active area or active cross-section of the microdiamond, it's also possible to vary the concentration of the boron within the sensitive area of this detector to even further improve the performance of this detector. And those two components, so changing the boron concentration and lowering the size of the active area, led to production of the new detector based on diamond, which these days is being called flash diamond. You can see there's this flash sign over here, maybe not so clearly, but that's already available product from the PTW for the research applications. I want to be a bit more complete and also mention that passive detectors are still very adequate devices for ultra-high dose rate exposure, especially the ones I'm listed here, due to the fact that they are dose or dose per pulse independent. And in fact, those detectors have been probably the most widely cited in radiobiological literature, which is demonstrating that they carried out traceable dosimetry. So several advantages of those detectors, but I want to, of course, point it out that those detectors are involving complex and time-consuming post-irradiation processing. They do require calibration for each batch. And of course, if the process of analysis is not well established in given institute, it can lead to large uncertainties. Now, Hans already did a fantastic work of demonstrating the principle of operation of calorimeters, so I will be able to skip those slides. So just will highlight again that the principle of operation calorimeters is relying on determination of the temperature rise in the medium due to ionizing radiation that is depositing energy in that medium. So that delta T is this quantity that we are and can measure quite accurately with adequate instruments. So I wanted now to give you an example of a possible application of much simplified calorimeters. I know everyone who thinks of calorimeters, they think of primary standard instruments, which are only available in primary standard labs, but it's possible to design simple calorimeters like the one we have done at NPL. This device we call secondary standard calorimeter. So even though it can operate and can provide absorb dose to water measurements from first principle, can act as active or absolute detector, our aim is to use it as ionization chamber. So calibrate it in against the primary standard instrument as ionization chamber. So in our case, we just designed this simple calorimeter to resemble something that is familiar to you, ionization chamber. In this case, external dimensions are being matched to PPC-05 ionization chamber, but the core part of the instrument is the graphite core, which has dimensions of 16 centimeter diameter and 2 millimeter thickness. And as you can see, this it is being embedded in a simple 3D printed body and only has one thermistor embedded in the core. That whole system can be made waterproof simply by lacquering. And as goes to the readout system, it's also quite a simple solution. You can see the realization over here. So our calorimeter looking like ionization chamber. We have here a small box which is housing Wheatstone bridge that is in, of course, the part of the system that allows us to measure the temperature rise. The whole system that we design is really coming with a simple 10 voltage reference power supply, and also in our case we have used a digital multimeter Keithley electrometer 6500, but there could be other solutions, more and less sophisticated, that could be as well used instead. But the whole system cost, just building the system costs about £1,000, so it's certainly comparable to ionization chambers. So how we calibrate them at NPL, so this is just a simple demonstration that we're using the same methodology as with the ionization chamber, and our secondary standard calorimeter is fully traceable to our primary standard electron calorimeter. So to test the performance of this instrument, we carried out measurements at ultra-high dose rate beam with a dedicated flash linac called electron flash linac, which is being manufactured by Sordina. And for this work, we utilized 9 NeV electron beam with a certain beam parameters, but I wanted just to draw your attention to this dose per pulse range that we have been investigating, where the higher range is, of course, relevant for the flash radiotherapy, and lower range is essentially something that is more resembling the conventional dose rate delivery. So the results that I want to show you, I mean, this is the typical calorimetric run for this instrument. You can see very sharp temperature rise, which means this extrapolation of pre- and post-irradiation drift in flash radiotherapy becomes much more accurate, and the determination of delta T, in the matter of fact, is burdened with much lower uncertainty for ultra-high dose rate exposures than in conventional radiotherapy. But the point I want to make is that there is great linearity in terms of measured and indicated dose per pulse, and essentially demonstrating that this system is dose rate independent. Sorry, I will need to rush a little bit at the end. We did also some comparison of this instrument against another totally independent system, Alanin, which is demonstrating that both instruments, which has totally different traceability routes, are having excellent agreement, and each of them can even measure those with quite good uncertainty. 2.5% at K equals 2 for secondary standard, and Alanin, in our case, can determine a dose for flash radiotherapy, electron beams with an uncertainty of 3.3%. So, okay, the last bit is related to some examples of application of primary standard in flash radiotherapy. So the first approach that has been proposed by colleagues from Germany, PTB, was to develop their own reference electron beams in their labs and utilize their existing primary standard instrument, which is water calorimeter, and carry out those measurements. So there is a paper published very recently by Alexandra Bourgon that demonstrated the performance of their primary standard water calorimeter with all evaluated correction factors that Hans has been referring to for ultra-high dose rate exposures. However, another approach which needs to be taken for different beam qualities which are not available in primary standard labs, like protons in the future, maybe heavier ions that can be delivered at ultra-high dose rate regime, is to take a primary standard instrument to a user facility and carry out the measurements over there. So that's what we've done at NPL. So we traveled to Cincinnati back at the beginning of 2020, and we used our primary standard graphite calorimeter over there. We just slightly reconfigured it in order to operate it at ultra-high dose rate and use it only in quasi-adiabatic mode. And we carried out measurements at flash proton beam with a dose rate of average dose rate of approximately 65 gray per second. This is just the configuration of the beam. And we disseminated the absorbed dose for a range of square fields with the uncertainty of 0.9% at k equals 1. So this is really primary standard measurement, but for flash radiotherapy. Additionally, going back to ionometry, we also compared behavior of a number of commercially available plane parallel chambers, correcting them for ion recombination in these beams. And turns out that a number of existing ion chambers with a sufficiently small gap separation, such as advanced Margus or possibly also PPCO5, are behaving well enough in flash quasi-continuous proton beams and could be used without any further alterations in terms of the development of new protocols or procedures. So quasi-continuous proton beams are much of a less of a problem for quasi-continuous proton beams. So this work we have done at Cincinnati has been critical for the FDA approval of the FAST-01 clinical trial I mentioned at the very beginning. And the last message I want to say that there are very important initiatives, and one of the ones I want to bring up is the ESTRO-AAPM Task Group 359, which is currently working on the development of recommendations for dosimetry for flash radiotherapy. So summarizing, flash radiotherapy is inducing much higher ion recombination effects, particularly for the pulsed beams. For ultra-high dose rate quasi-continuous proton beams, some ionization chambers are exhibiting effects of ion recombination that is still within the requirements of the codes of practice, within 5%. However, they usually are burdened with larger uncertainties. As I have demonstrated, there have been already new detectors developed with improved linearity as a function of dose per pulse of dose rate. However, the reference dosimetry hasn't been established yet for those instruments. Several passive detectors, which are dose rate independent, are still very promising tools for dosimetry in flash radiotherapy. However, they are less practical for daily routine. I have demonstrated that there have been already approaches of employing primary standard instrument for flash radiotherapy dosimetry. However, we still do need international codes of practice in order to demonstrate international comparability. And codes of practice for dosimetry will be essential for safe implementation of this new technique for clinical practice. Thank you very much, and I'm sorry for running a bit.
Thank you, Anna, for a very interesting presentation with a lot of content and keeping to time. It's amazing. There's also some time for some questions from the audience. Anyone? Let me get the microphone to you if you want to put your hand up to ask a question. Any questions from the audience? Weibo?
I have no question. I just want to get some information from you, maybe. You introduced a very detailed dosimetry, but the flash effect, I think, because if we look the Hans, the scaling, the time scaling from the effect, it can be also the chemical effect, about 10 to minus 10, I don't know. What do you think the dosimetry related to effect, or you plus some the effect of the chemistry?
Yes, so I mean the current trend or preference is to really understand as well very well our temporal beam structure. So I brought up that most of the work that has been done with pulsed beams, but there have been a number of papers as well published with a synchrotron. So these are not considered to be, pulsed in the matter as electron beams. So what I want to say, that the flash effect has been demonstrated for different beam temporal structures. There have been some attempts trying to quantify whether this temporal beam structure will have an impact on the biological effect. My gut feeling, again, I'm a physicist here, is that it will. But one of the main points as well I want to make is that that's why it's so important to really understand what we are delivering, not only in terms of, as a concept of dose, but what we are delivering in terms of, is it one pulse? What is the pulse duration? Is it 4 microseconds? Is it 2.5? Has it been delivered with 2 or 3 pulses? There is some indication that delivering lower number of pulses but with higher dose per pulse may have increased effect on the flash, this flash effect. However, the research is still ongoing. You are very right. I don't think it's something from the point of view of biology that is only going into the biological effect. There are probably some mechanisms already at the early physical, chemical stage, that will be impacting that biological effect, which we call flash. But again, probably in a few years' time, there will be somebody here, some biologist standing here in front of you and saying what the flash really is. But at the moment, the answer is we don't know, and we need to really see.
Thank you for a very nice presentation. I have 2 questions. First is about the boron content. One, why the boron content changes the response of the diamond detector?
Yes, I think I'm not an expert in microdiamond dosimetry, but boron content apparently has that effect of limiting or decreasing, or suppressing the response of microdiamond. And essentially, apparently, the kind of a best way to really optimize this linearity, because that's the problem as a function of those proposed, is by changing the boron content, which is suppressing the response. So essentially, what you see is a lower output coming from the microdiamond, which is doped with extra boron. So that's. But another way to do it is, in fact, to decrease the size of the sensitive area, as I mentioned as well. So this is this kind of a double effect, which is leading to a lower signal. That's why readout of the flash diamond is slightly different than what we are using currently for conventional radiotherapy.
Thank you. And second question is, are you working on 2D dosimetry also?
Yes, I mean, yes, and 2D dosimetry will be critical, and also from the point of view of development of adequate beam monitoring instrument as well. From this point, I didn't even touch upon it because it was such a limited time over here. But we can have another talk just on 2D dosimeters, and they will be incredibly important because, let's face it, very often, especially the research beams that are being currently used for flash radiotherapy, they are not beautiful homogeneous beams. They very often have some sort of Gaussian distribution, God forbid, some heterogeneities, which are even more complicating the situation. So yes, 2D monitoring is very, very important. These days, most of the researchers are really sticking to established methods, radiochromic films, which can provide this 2D dose distribution. However, of course, we want to have some active detectors that can provide us on-axis information about 2D dose distribution as well.
Thank you.
Thank you, Anna. Of course, I'm sure that the speakers will be able to take more questions in the coffee breaks, and you can pester them there as well. So, just Kirsten, change the slides. So the final speaker in this session is Niels Bassler from the Danish Center for Particle Therapy, speaking behind me. Especially fractionated radiotherapy, grid therapy. What are the dosimetric challenges? A long title, I couldn't remember that one in my head.
I reduced it a bit shorter, right? So I left out the good part. Yes, I'm going. Yes, from
full screen. Do you know?
Full screen? Yes. No, actually not.
PDF. I'm not sure.
How? Yeah, I use Linux, right? So I don't know.
But it's fine. I think.
Can I go to the
This
next?
one.
Lilka, please help me. Okay, anyway, so, sorry. So what I would like to do is to tell about well, we're going now from temporal fractionated to spatial fractionated therapy. And what I would like to show is like make a very little overview of it, and I'm not going to go so much into the biology of it and so on, but then try to highlight some of the dosimetric challenges which we have there. And then I'm going to show a little trick, what we did in order to circumvent all the tricks at DCPT, where we did some preclinical studies already, where I'm going to show some of the very first results, what we ever achieved over here. It's not published yet, so it's actually quite interesting what I'm going to show you at the end. This work, I would just have to say, it's not me alone, it's also with my PhD student, Fardus Reas, and Lina is a pointer here somewhere. Yes, there is. Lina Brito, our biologist, and Erik Tranius from research. Okay, cool. Spatially fractionated therapy, well, here's a sort of rendering what this is all about. You have some sort of radiation coming in here, you have a collimator, and then you have like all these beamlets appearing on the other end. So we are actually spatially fractionating the beam along the lateral axis. And then you can choose to deliver a heterogeneous dose to the tumor as well as to the normal tissue, and apparently it seems so it has a very profound effect on the normal tissue damage and also the tumor control. The idea is not very new. It's actually quite old. It dates back to more than 100 years ago, where Albert Köhler, he published a paper where he, at that time you had only low voltage X-ray radiation, and if you wanted to treat a tumor which was seated somewhat deep, then you were kind of limited what dose you could give to the tumor simply by the surface dose to the skin, since it was low voltage. So you would simply burn the skin this way. And Köhler, he came up with the idea, well, let's make some sort of a metal mesh or skin and press it on the skin. And then suddenly he discovered that, okay, this maximum skin dose increased many times than what it would usually be able to tolerate, all the way up to, well, retrospectively calculated 60 gray. You didn't have grays at that time, so some people figured out. Okay. And also skin necrosis healed in several weeks simply because you had these little holes there. Some pictures were then appearing in a paper from 1934 from Wilhelm Haring, where he treated 20 patients with what he said corresponded to 5 gray skin dose. He was kind of unspecific on the outcome regarding with tumors, but he was more concentrating on how the skin developed. And again, he observed that it was extremely well tolerated in this one, so that sparked some motivation to look into this more. However, we got up to higher voltages, we got mega voltage radiation, Linux and so on, and then suddenly this entire problem with the skin toxicity disappeared because we have the build-up effect of these mega voltage radiation. So this spatially fractionated therapy or grid therapy actually completely disappeared for some time, and there was only very limited activities around this. Now, in the 90s, it began to resurface again as an idea how to shrink very bulky tumors, as shown in here, for a large tumor which is growing at the side, where you simply give, again, several small beamlets of this in order to shrink it. This was a case where you simply couldn't deliver the entire dose at once because that would cause too much toxicity, but it was meant as a palliative treatment, so simply to reduce the tumor size. And it was again very well tolerated in this time, and actually later on there were also some results which proved to be very encouraging. Now, before continuing on, we have to separate spatial fractionated therapy into several subgroups. So conventional therapy, I mean, this is supposed to be, this is from a paper, this is supposed to look like be a tumor, and you have a homogeneous iteration in conventional radiotherapy. In grid radiotherapy, we're talking about centimeter-wide beams. And this is both actually in clinical use already, albeit very rare, but it is being used in mostly palliative cases occasionally. Then we have even smaller beamlets. That's if you are about 1 millimeter down to 100 micrometer, you refer to this as mini beam therapy. And even smaller, like micrometer stuff, obviously we call it microbeam radiotherapy. This is not used clinical at all, but preclinical studies are ongoing. Starting from the back end, we have microbeams. So these are very, very, very small beams. And what you also can see here, that is that if you irradiate, in this case, some sort of brain tissue of mice, they were irradiated with very 100 keV, very intense synchrotron photons. So it could be facilities like Grenoble or so on. And they see that the brain was able to withstand doses up to 180 grays peak dose, which is quite large. However, since these very, very narrow beams, we are very sensitive to cardiopulmonary motions issue. The tissue simply blobs with the heart beating, and you want to have the beam that's always, don't want them to wash out as a function of time. So it was also combined with a very, very high dose rate. So actually what's going on here is flash and microbeam radiotherapy all in one go here. Another example that we're irradiating rat brain tumors, that's actually what we have here, where the entrance dose was again crazy high, 625 grays per microplane, and the tumors disappeared even if they irradiated for single plane irradiations and so on. So it looks like very strange biology is going on here. And going now to mini beams, there were also several preclinical studies, and there you see something similar, even if the peak doses are lower, that you see like something like 58 peak dose, and you can still see good tolerance in normal tissue and so on. I've tried this also with protons, carbon, oxygen, ion beams, even neon ion beams, and there are several things about that. Grid protons, I also wanted to mention here, you have a tumor which is being irradiated with several beamlets from a prototherapy facility, again looking like this, and again it was always with a palliative intent, but they see again a quite remarkable effect of it, and that the patients which have been treated occasionally actually live much, much longer than was even expected from palliative care. So it gives the idea that maybe this could also be used in a curative intent. Okay, that was the background. Okay, what's going on here? This is some sort of a volume effect which is in there, and I'm not going to talk about all the biology about it because it's a lot. But basically the idea is, I mean, some sort of a volume effect. The smaller volumes you irradiate of a tissue, the higher doses it tolerates. This has been shown many times, in this case, for instance, for our rat spinal cords, which have been irradiated, and the doses are simply much higher before you produce a side effect as a function of irradiated length. Okay, one more note I have to make, that is that there actually the discipline of spatial fractionated therapy splits the community a little bit. There are those who believe, yes, we can deliver a heterogeneous dose to the tumor and achieve tumor control and tissue sparing. And then there are those who believe, yes, no, it's better to start with homogeneous tumor and then just keep this as a fractionated part in the entry region. So I'm with the second team here, and I will show you that's also why later. Good, but that said, with grid, you can even make some fancy interlacing where you can achieve nice homogeneous tumor coverage by simply interlacing the individual beamlets from multiple fields. So you can achieve a homogeneous tumor coverage over here. Okay, that's a lot. Now let's step back a little bit. So what is radiotherapy actually about? Well, first of all, we want to achieve tumor control. Well, that's easy. We can take a tumor, we can irradiate it, and as we crank up the dose to the tumor, eventually we will always achieve tumor control. But in reality, of course, this is not possible because we have the healthy tissue around it. And that's here the red line, normal tissue complication probability. So, of course, as we increase the dose, at some point the normal tissue is going to make severe toxicities, and we cannot deliver the dose which we wanted to achieve tumor control. Now, if you subtract these two curves, then we have the blue curve, which is the tumor control probability without complications. Now, the entire idea about finding new modalities and so on, we want to increase this therapeutic window. We want to have a therapeutic gain, so we increase the sweet spot, which we have over here, where you have the highest chance of tumor control without complications. Good. What does this mean for grid? Well, first of all, what do we have at the x-axis at all? I mean, dose. What do you mean by dose in this? I mean, we have all kinds of different values everywhere. So that's already a complication. We cannot produce these plots for grid therapy because what is our x-axis simply here? Okay, and that brings me back again to this little overview. We have conventional therapy. Well, okay, we are classifying all our treatment plans as a function of dose in the tumor, for instance, and we can look at the dose in the normal tissue. Ion therapy, it already gets a little bit more difficult. We heard also in the first talk, there were briefly mentioned RBE. For proton therapy, we assume a RBE of 1.1, and we begin to realize, that may not be exactly true. It looks like we have some severe toxicities at the end, which sometimes may need to be accounted for, so maybe we should use a variable RBE. This discussion has now been going on for 20 years in the proton community, and we have still not continued from this part. Now, go to SFRT. Well, dose, yeah, but what dose? Where? Peak dose, valley dose, average dose, I mean, all kinds, we don't know. Center to center distance, yes. Do we need to have wide spacing between the beamlets, or can they be narrow, or how narrow, and so on? What period should the apertures have of the collimator? There's both the scepter and the aperture, which doesn't have to be 50-50, it could also be 20-80 ratios, and so on. My point is, we are introducing a lot of new degrees of freedom over here. So this is very, very difficult to figure out. What is the sweet spot here? What are we trying to aim for? So what values are typically reported in SFRT? That is like peak dose, valley dose, collimator width, and collimator spacing. Average dose is often being used, and then a concept which is called PVDR, which is the peak to valley dose ratio. It's a measure of contrast, okay? So you can have apertures like this, you can have slit apertures and so on. I just took some random ones I found on the web just to show it. And here you get patterns like this, where you have a peak dose and a valley dose and C2C. So, and this is what, yeah, just an example how it's being reported. It's taken from a paper, and then you can see they report, like it's a retrospective study, peak to width of the collimator, peak dose, and PVDR is also here, and so on. And that brings me to the actual point of my talk. What are the dosimetric challenges? Okay, still coughing time, 50 minutes, yeah. Okay, good. Let's start with peak dose. Okay, here is a special fractional dose pattern from a publication I took, and we can see there are 5 peaks, right? What is a peak dose here? Is this a peak dose of the highest peak? Is it of the average of 2 peaks, 3 peaks, all peaks, right? I mean, you can make any number out of it, right? And this is at a certain depth. It may change also at a different depth and so on. So what do you mean by peak dose? Okay, that's one thing. Same thing with valley dose, of course, and so on. Next thing is also, are you able to sample, are you doing the sampling properly here? Oh yeah, this is another example of what we have here. This is actually from one of our own collimators, where we actually looked at the effect if we are slightly misaligned. Then you can see that we gradually also changing how the valley doses and the peak doses change. And again, I mean, even if you're perfectly aligned, it will not be, the peaks will not all be the same, right? There will be some variability here. And so again, what do you mean by peak dose? What do you mean by valley dose? Regarding the sampling, I have this little slide here. So you can do Monte Carlo simulations. You say like, okay, we have a special fractionated theorem, and this is a peak dose. I can get it from the Monte Carlo simulation. You have to be careful what voxel width you take here, because if it's too large, then you are averaging over something, getting a number which is lower than the actual peak dose. Dose itself is a point quantity. And what you're trying to get is the expectation value by averaging over a sufficiently small volume. So this is for a 2 millimeter center-to-center collimator and so on. And you can see if you make your voxels too large, then suddenly you get, you're averaging over several slits and so on. You get different values for the peak dose as if you make it very small, but that takes a long time. So actually you're making something like microdosimetry here if you look at it like this, because you have a large, let's say, scattering from the many different Monte Carlo simulations, which are long, in order to reduce the uncertainty for the results to converge. But obviously the peak dose would be something along this line. Most papers I see about this, they don't even show that they are in a proper region with the voxel scoring, and I suspect that many of the values which are reported are actually somewhere on this edge here. Same thing with valley dose. Average dose is also weird. I mean, there are two things about average dose. First of all, average dose itself is not really a good predictor for what is going to happen radiobiology-wise, because what you can see on here some examples of some configurations where you in all cases would have the same average dose. But clearly this is probably not going to introduce the same biological effect in these times. So average dose is a quite poor predictor for a biological effect. Now the next thing is also, what exactly is it what you're averaging? Are you averaging over one period? Are you averaging over several periods? Are you averaging over the entire volume of the target tissue? Or are you averaging, let's say, a non-integer fraction of the slits and so on? Again, there's no consensus on how to do this in other ways, and depending which way of average you do, you would get different values, even if it's the same configuration you're talking about and so on. So that's also an issue which we have there. Center-to-center distance is often reported, and they take this as the center-to-center distance of the collimator, but that's not necessarily happening in the body. All beams, what we are working with, well, most beams, they are divergent in some sense. So you can see the center-to-center distance is actually varying as a function of depth, as we spread out, and it may be biologically important, and that's also something which is not really taken into account. Oh yes, and this is a technicality, something which I also a little bit annoys me. That's a peak to valley dose ratio, which they use a lot. First of all, they're taking the peak dose and valley dose, which I just try to argue is not well defined. And then they use this ratio to say something about the contrast, whether we have no grid or whether we are totally grid. Then, oops, yeah, it goes to infinity. Yeah, because if the validity goes to 0, it's divergent. I mean, PVDR, what is the significance if you have PVDR 537 or 5,939? I mean, its value dose is close to 0, and it's like, I mean, good numbers, they should somehow relate to an observable in a nice way. But this is like a number which is wildly fluctuating for something which probably has no biological impact, whether the dose is 0 or close to 0 and so on. Fix is very easy. Take the inverse, the value to peak dose ratio, and that's when then you have something. You have a number 1, which is no grid, and 0 if it's totally grid, and that is something a smooth varying function. However, this is rarely being used. The community sticks to PVDR all the time and reports these crazy numbers if the value dose is 0. Even if you have Monte Carlo simulation where you get 0 dose, you can't. I mean, how you get infinity or not a number out of it? It's a little bit strange. Dosimetry, how to measure dose. I mean, we need small detectors, diodes, diamonds, and so on, and then welcome to small field dosimetry. This is actually an extension of small field dosimetry, I think, and this means that we have a lot of problems. We have no lateral secondary equilibrium. It's easily broken in these cases, and so on. So I think it's, I mean, it's problematic to get values about it. There's very little research done about this. I found one paper from 2012 where they tried to do it for X-rays, look at scattering factors and so on. You do lose a lot of films, which are correction-free, especially. That's very nice. So but you can only get relative dose about it. Films also quench, they saturate, there may be interbatch variations and so on. And the accuracy, what you get from films, well, K equals 2, on a good day, maybe 10% or so. But the thing is that if you ask people doing film dosimetry, they're mostly not aware of it. I mean, you can go to anyone in the mini-beam community and ask, oh, how good do you think your dosimetry are? And, 4% maybe, and so on. And, yeah. Okay, anyway, so here's the solution. Real-life example, preclinical research to DCPT. I don't have a solution to any of these things, right? I'm just presenting them here to inspire something to think about and so on. Perhaps we can make something out of it. But we try to circumvent all these problems by doing a little trick, which I'm now going to show you. So we are still interested in this, and we wanted to do a special fractionated theory. We were looking at proton mini-beam therapy here now, and we have a radiobiology lab, and what we wanted to do, that is we wanted to compare conventional proton mini-beam therapy with proton mini-beam therapy. And the problem is, right, okay, how are we going to do dosimetry here? Well, the solution is we are not going to do dosimetry over here. So the thing what we are doing instead, that is that we are simply relying on the dose in the tumor alone. So our goal is that with this collimator, we need to be as homogeneous as possible and as comparable as possible to the conventional. And this is going to be, let's say, our point of reference over here. So we say for the same tumor dose, what we want to show that is that we have reduced biological effect here compared to the conventional, right? Because we need to show that mini-beam radiotherapy is going to be an advantage. So first we check, of course, for homogeneity. We put EBT films in here, and yeah, it's heterogeneous here, and okay, we are fairly homogeneous here, so we are sure we got that right. The mouse foot positions, we would like to have, you know, like just at the start where the contrast is highest. So this is like a probe for normal tissue damage, and we use acute skin toxicity here in order to probe it. So the hypothesis simply is that we will see less damage here than here for the same tumor dose. We did lots of dosimetry then again in the PTV just to ensure that we are over here. So you know the solid line, this blue line here, this conventional depth dose curve, what we have, that's fine. We put in our collimator, and then suddenly we have the red line. No, this does not make sense, as I said to you. We can't measure dose in the heterogeneous region. But in this region we are homogeneous, so here we can measure the dose. And well, we get reasonable values out of it. And we can see there's a slight angle here on the spread of Bragg peak. That's because we have some nonlinear absorption of the energy layers in the collimator. We correct for that, and then we get the green line here, which is pretty much on top of the blue line here over here. So we can now prove that we are dosimetrically equivalent in the spread of Bragg peak, so which is our point of reference. That's cool. This is just a heterogeneity. We are trying to measure this as well, and we can see, okay, we are within acceptable limits, and so in the PTV, this is at the entry region. Good. And now here comes the trick. So we are going to do first a response curve. This is normal tissue complication probability as a function of PTV dose for leg toxicity model, which we insert exactly in the PTV. This we know, this is conventional therapy, there's no grid here, and we get a nice sigmoid curve. No surprises here. This is exactly, we have done this many times before, also for other experiments. Now we introduce a collimator, but since we know what the dose is, and is exactly the same as it is for the reference case, we expect that these two curves are going to be on top of each other. So this way we have proved, yes, we have two equivalent situations in the hypothetical tumor volume. Now, if we are going to move the mouse leg into the entry region, and again without the collimator, so this conventional, we expect to have a new curve as a function of PTV, which is moved to the right, simply because we have a lower dose here for every dose what we have here. We have roughly 50% of the dose here. That means that this curve is going to be shifted by a factor of 2 roughly to the right. Okay, and now comes the point. We remove the collimator and then we do the same thing again, and if our hypothesis is true, then we expect that we can increase the PTV dose even more before we see the same amount of damage, right? So if we would have 50% damage conventionally, it should be reduced. That means we can increase the PTV dose to get somewhere here. It's a bit convoluted, but I hope you can follow me. I really try to take you through this very slowly. And the cool thing about this is that, ta-da, we have something we now can quantify. We can establish a grid factor. We can take, for 50% NTCP, we can take the ratio of PTV doses in the case where you have no grid divided by the case where you have a dose in the PTV. And we can do this for ESO effect. We are not relying on any ill-defined definitions of dose. We are just looking at the PTV dose, which we have in here. And this is actually making it extremely robust and completely unambiguous. Which we think is actually quite cool way to do this. Grid factor is actually looking very much like the RBE, which Rabus also showed in the first presentation. We have a ratio of doses, we have ESO effect, and it behaves also, should also behave like RBE. It's endpoint specific, it varies as a function position, where you are going to probe it, and so on and so on. And it's a value you can directly multiply with a PTV dose as well. So it's something medical doctors could work with even. So if we had a grid factor of 0.5, it means we would see, we could double our PTV dose before we have the same damage in the normal tissue. And this would also scale nicely with the VPDR division, by the way. That's another bonus thing, but yeah, okay. Cool. So we did this actually. We irradiated 75 mice with grid and without grid, and first time, these are our results. This is the first time I show this, right? So I'm so proud. So what we are seeing here, there's no TCP data. There's only the NTCP data, which we are showing in the entry region. This is showing our response curve in the conventional case as a function of PTV dose for mice legs at the entry region. So this is what we would expect from normal therapy. So we have the sigmoid shape and so on. And when we put in our collimator, then we see this, what we have over here. So we see there's something which looked like the start of a sigmoid curve, but when we went to higher doses, then suddenly we were not able to see any score 2 toxicities, which is reddening of the skin, basically. Reddening of the skin is not a very severe toxicity. 2.5, score 3, and 3.5 are more severe toxicities. We did this as well. We were also monitoring for that. And from all the mice which were irradiated conventionally, we of course saw these higher toxicities, again, as expected, more or less where we thought they would be, like between 60 and 70 grays for score 3. But when we did this with the collimator, we saw 0. We did not see a single mouse developing any of these severe toxicities. We almost doubled the dose in the PTV, and we did see nothing. So we were not able to get a grid factor from it, simply because we saw nothing to score, simply. And that is kind of staggering. It's a fact which is bigger than the flash effect, so we are very surprised to see this. What I wanted to say also, that is, we would like to go higher, but we are simply limited by our cyclotron. We cannot give higher doses at the moment. We have an 8-minute limit, so this is like 8-minute full power, 550 nanoamps and so on. And then we have to have a little cool down, and we didn't want to do this because this makes some radiobiology effects and so on. We try to give everything into one go. Yeah, so that was pretty much what I wanted to say. Summary, just what I said. Especially fractionated therapy has drastic normal tissue sparing effects, could be very important, and it's not only limited to what I just showed you, proton therapy. I think it could also be a big, a new important thing for conventional X-ray radiotherapy. However, we introduce an enormous amount of degrees of freedom, peak dose, valley dose. What separations do you do? In our case, what we did here, it was quite simple, because we wanted to be homogeneous in the PTV, we wanted to be heterogeneous outside of it, and that we could use for optimization, so we could try to be as coarse as possible and have as large contrast as possible by trying out many different materials, configurations, and parametric study. It took 2 years to do that, probably. And then we found a sweet spot where we think we could get, let's say, the most bang for the buck. However, if you are going for a heterogeneous tumor dose, then we have no guidelines what to choose and whatsoever. So I think when I go to the medical doctors and say, hey, this is a potential new therapy, let's try it out. We say that the doctors are going to look at the heterogeneous tumor dose and say, nah, I mean, you can't cure a tumor if there's no dose in here, right? So what are you showing me? And that problem you avoid by going to a homogeneous tumor dose, because we are able to cure the tumor, no problem, but we have this special going on here in the normal tissue, and we can show from mice experiments that it looks like we can drastically reduce the side effects. Yeah, so yeah, but dosimetry-wise, this is an extension of small field dosimetry. There are no protocols whatsoever over here, so that's something where we need to just get started on, and we need to think also about what we're going to do. So yeah, and even if we did this trick by using homogeneous dose and having this grid factor, we still need to somehow be able to characterize the very heterogeneous dose environment before the TCP. I don't know how to do this. So that concludes.
Thank you, Niels. A very interesting presentation. I knew nothing about most of that. We've got time for some questions. No one really needs coffee after last night's dinner, do they? So Pavel.
So congratulations. Congratulations not only for the excellent presentation, but also for the work, for this experiment you did. Yeah. And as you said, there are many questions, not so many answers. Yeah, but one of the things that is bothering me is that the problem is, if in the proton therapy, the main problem is the toxicity of the skin. Yeah, there are of course several other methods like arc therapy, arc proton therapy, and so on. You shoot from very, very many directions and with the different energies and so on, and you spare the skin anyway. Yeah? But so the question is the grid therapy the best for toxicity, but having the target volume with a constant uniform dose, or really, as it was shown in Chicago, you see to irradiated large volumes, you see with separate beams there. So I would say that the toxicity of the skin could be solved by the arc therapy or other part of this. Because here you are always showing here you are always showing single beam, yeah. But if you put the multiple M beam, you see optimization and so on. You could get quite let's say good dose distribution and also a relatively low dose of the skin. But I would say these irradiations in the target volume with separate beams, which That would be, so non-uniform beam, that would be an interesting option.
It would be certainly interesting, right? But here we are thinking translational at the DCPT. We just want to find something which we can use, well, as soon as possible in the clinic, basically. I think before we have sorted this out, how to construct our dose in the tumor, I don't know what will be first, that or the fusion reactor. I mean, but that said, one misunderstanding I just want to clarify. We use a skin toxicity model to probe for NTCP, but we don't care about skin toxicity in the treatment, because that's not what we are aiming for here. Skin toxicity is rarely an issue. We are looking at more deeper seated things, which just like any organ at risk, which might be there, the brain, right? If you treat head and neck cancer there, you want to minimize toxicity in the brain by using this. Say again? And so the contrast diminishes in there. There's another issue which is completely unaccounted for. That's, can we fractionate this? Can we deliver this in multiple fractions? Because if we can't, then it's kind of pointless, because fractionation is very important, which gives a big therapeutic advantage. Typical thing, right? You have this wonderful new modality which has this big effect, but we have to, in order to use it, we have to give up another well-established effect which is regularly used in radiotherapy. And then what have you got? Probably nothing. Same thing with
I know we've got at least one question online. Someone's spent half an hour typing in a fiendishly difficult question for Hans. Any more questions? We're eating into the coffee break a little bit now. I'm sure the speakers are available to answer questions in coffee. Any other questions?
So we have still one question online for Hans. Oh, I see coming in another question for Niels as well. Please stay. There's a question from Yun Yong Kim. Thank you for the presentation. I would like to ask one question. I guess all the experiment was done using synchrotron to make pencil beam. Have you tried the conventional source that can't make pencil beam, mini beam radiotherapy? One of the advantages is that design collimator can make mini beam patterns without using synchrotron. I expect this hypothesis make it harder to measure dosimetry.
I have to read that question myself. What was that?
The second one.
So first of all, only the microbeam experiments were done with synchrotron radiations. We have a cyclotron for proton beams and so on. The beams are much larger. And okay, what are you writing here? Have you tried conventional source that can't make a pencil beam? Oh yeah, X-rays. That was actually one of the slides at the beginning I showed. For X-ray mini beams, you can use a collimator and then simply use X-rays for that. However, you won't achieve homogeneous dose in the target. Yeah, and I hope this is more or less what your many questions were about. Otherwise, send me an email and I will be happy to discuss with you.
Okay. Yes, we had one question to Hans from Frank Ehmart. What are the radicals of the chemical heat effect in a calorimeter entirely filled with water? An example, is the chemical heat effect in the end material specific when you go to biological tissue?
For water, it's basically H2O2 mostly that is formed there. And of course, if you have impurities in the water, which you usually have, you can also have chemical compounds formed from that. So that was the first half, and the second half for the biological systems, basically you can have a host of things. I mean, basically any break of the DNA or of any proteins or membranes, these are irreversible changes. I mean, they're not completely irreversible, but some of them are, and is actually where the deposited energy goes. I think that was about, right? Okay.
Yeah. Well, thank you very much to the speakers.
And anyway, if that was not the answer, please send me an email.
Thank you very much for the speakers. I certainly learned a lot in that session, and I hope others did too. There's coffee across the corridor here. Can we try and get back in for 11 o'clock for the next session to start? Thank you.
I want to see something now.